A sudden, severe sandstorm rolls across the Middle Eastern desert and brings heavy machinery to a dead stop. For a massive crude oil pipeline project, work on the trenching phase freezes instantly. Delays like this occur in almost every engineering, procurement, and construction megaproject. Extreme environments, permit hurdles, and complex stakeholder networks mean the schedule will fracture at multiple points. When a project misses its completion date, the financial consequences are immediate. Contractors and clients find themselves facing millions of dollars in disputed liquidated damages, arguing over who is liable for the overrun. A single retrospective analysis at the end of the project often fails to resolve these disputes. Attempting to audit the entire timeline at once conflates overlapping variables, making it difficult to separate a client-caused material shortage from a contractor-caused labor dispute. To isolate these events, we use window analysis in Primavera P6. This method slices the total project duration into discrete chronological intervals. Breaking the schedule into individual windows maps the exact moment a delay enters the logic network. We stop looking at the project as a singular block of time and start evaluating exactly what happened between day 1 and day 30. This chronological isolation turns subjective negotiations over delays into empirical evidence. It builds a data trail rigorous enough for formal arbitration. To see how this forensic breakdown works, we'll apply it to a 120-kilometer crude oil pipeline. The scope requires sequential phases: route clearance, trenching, pipe laying, welding, testing, and backfilling. Step 1 establishes the baseline schedule, a logically linked network acting as our reference standard. Future variances are measured against this plan. Step 2 defines analytical windows, dividing the project duration into specific chronological intervals: Window 1, Window 2, and Window 3. The size of these intervals is determined by the project's reporting cycles or the major contractual milestones dictated by the project documents. For most EPC megaprojects, monthly update windows are used. This syncs the forensic analysis with the commercial rhythm of monthly payment applications and progress reporting. Slicing the schedule on arbitrary dates ruins the analysis. If the windows do not match the actual dates when field data was gathered, the logic model becomes disconnected from the project records. By establishing a baseline and slicing it into verified reporting cycles, we restrict complex, overlapping project variables into single, manageable timeframes. With the model built, we move to execution tracking. This is where real-world progress intersects with our planned logic. Step 3 updates the schedule by setting the data date, the exact cutoff for Window 1. Field actuals are entered into P6, start and finish dates, remaining durations, and % complete. Step 4 saves a discrete snapshot, locking the project state. Failing to save clean snapshot files removes the data trail. Writing over the previous month's schedule deletes historical timeline data, making forensic backtracking impossible. As actual dates overwrite plan dates, delayed activities consume float, the buffer time before an activity delays the project. Step 5 identifies the new critical path. Recalculating the network reveals the longest sequence with zero float, highlighting the driver of the end date. This recalculation frequently exposes path shifts. An activity that had buffer last month might consume all its float and become the critical task driving the final deadline. Capturing sequential snapshots preserves this volatile scheduling data. It locks the evidence in place before the next update cycle changes the history. During Window 1, heavy industrial trenching machinery abruptly stops. The bucket strikes an impenetrable layer of solid subterranean bedrock, halting progress. Applying steps 6 and 7, we compare actual trenching against the baseline. The rock excavation extends the activity, exposing a 4-day variance that shifts the critical path. Step 8 assigns liability. Because excavation falls under their scope, this is categorized as a contractor delay. In a sprawling desert staging yard, welding rigs sit parked and silent. There are no steel pipes left to weld. Advancing to Window 2, we measure progress strictly against Window 1's snapshot to isolate the new problem. The material shortage adds 6 days directly to the critical path. Procuring the pipe was a client deliverable, making this a client delay. During the final phase, industrial pumps sit dormant beside the completed steel pipeline. Hydro testing cannot begin without local water extraction permits. Moving to Window 3, comparing hydro testing against the previous snapshot reveals a 3-day permit delay. However, because hydro testing had sufficient schedule float, This external delay absorbed the 3 days without shifting the ultimate finish date. It is categorized as non-critical. Without window isolation, the timeline shows a project finishing 13 days late. The client and contractor would argue over a single 13-day period, rather than addressing 3 distinctly attributable events. Step 9 documents the findings. This table aggregates the isolated delay data into a comprehensive final report, classifying the exact activity, duration, impact, and responsible party for every window. The visual clearly displays the disaggregation. Out of 13 total delayed days on the project, 4 days belong strictly to the contractor's trenching issue, 6 days belong to the client's material failure, and 3 days map to external factors. External delays like weather events or government permits are isolated carefully in claims. They frequently grant contractors time extensions to avoid penalties, but rarely result in financial compensation. A claims board will reject an analysis if methodological mistakes are found. Altering the baseline mid-project or ignoring shifting logical relationships between activities will invalidate the findings. Maintaining the integrity of this evidence requires utilizing rigid activity codes in P6 to track delay reasons and backing up every data entry with verified daily progress records from the field. When the disputes settle and the final segment of pipe is buried, the financial outcomes rely on the quality of the data. Window analysis converts raw software scheduling into a verifiable data trail, isolating exact liabilities in a complex, overlapping world. To master advanced project management techniques and learn how to execute delay analyses, subscribe to the Agile and Hybrid PMC channel.